So welcome. Today we're going to talk about radical polymerization. If you recall previously, we talked about how radical polymerization can be broken down into 3 steps. And those 3 steps are initiation, growth of chains, and termination. And we're going to talk about a strategy for reducing termination. So we're going to talk maybe at the beginning about free radical polymerization. And then we're going to talk about this strategy to reduce termination and improve or increase the molecular weight of our samples, and that is going to be via a process we'll call ATRP, or atom transfer radical polymerization. And we're going to talk about why that might be better than just free radical polymerization. Okay, so let's start at the beginning, right? We'll talk about the first step of radical polymerization. We'll talk about initiation. So how do we initiate radical polymerization? Well, we create radicals. So this first step is initiation or creation. Creation of radicals. And there are many chemicals or processes to create radicals, and we'll talk about just one of them now, one such chemical process, and the initiator will be benzyl peroxide. Sorry, benzyl peroxide, it's a P. And what does it look like? Well, it's a molecule that looks like this. Oh, there's a benzyl ring right here. This is connected to a carbon here. There's an there's a peroxide bond in the middle, an O connected to another O. That's the key to creating these radicals. And then there's a sort of mirror image on the other side. You might have heard of benzyl peroxide in a couple of other contexts besides just radical polymerization. It turns out benzyl peroxide is a drug used to treat acne, and the creation of these radicals can help suppress the growth of bacteria and also help clear up some oils and stuff like that. But in our context, we're interested in the creation of radicals from benzyl peroxide. So peroxides in general are characterized by this OO double bond. And if you cleave this double bond, and there's sort of symmetry to the overall molecule, when you cleave that bond, you end up creating 2 similar molecules. So these are mirror images of each other. So you still have this benzene ring right here, and we have this carbon right here that's still double bonded to this one oxygen over here, and then single bonded to this oxygen over here. And there were 2 electrons that belonged to this peroxide bond, but when you cleave it and there's this symmetry to it, you just have 1 lone electron hanging out there. And it's like, oh geez, what am I going to do? Well, we know that electrons definitely do not like to have, or atoms do not like to have electrons with single electrons in an orbital. These are highly reactive, and that's the nature of the creation of this free radical. So how do we get that, right? This molecule doesn't necessarily want to break up on its own, so you need to usually kick it off with something to break this peroxide bond, and usually that's done with light or heat. This is nice that it doesn't just do it on its own all the time, that we have some sort of process that we can control to start off this initiation. So as engineers, we like to control this. So we can not have any polymerization happen. We can turn on the light. A bunch of polymerization happens from the creation of these radicals. And then our polymer is then created in the shape that we wanted. Or we could do a similar thing with heat. So, this is the first step is breaking of this peroxide bond with light and heat. Almost immediately, this this carbon right here pops off the benzene ring. So we get two of these rings, and I'm just going to sort of draw the shared electron orbital there, and we just have one, and our radical stays with this benzene ring, and we also get 2 CO2. So we get two of these rings with a free radical hanging out, a single electron unpaired, and then we also get some CO2. So sometimes people refer to this as pH or phenyl, because phenyl is the chemical, the organic chemistry term for like a benzene ring that has one thing that's hanging off that's eventually going to get bounded to stuff. Or in general, we might just call it a radical, which would be like R with a little dot. So it might be phenyl with a little dot or R with a little dot if we're talking more generally. So this is what happens. We have a mixture of our whole bunch of polymer monomers, but also some benzyl peroxide in there. We kick off by breaking this peroxide bond. We create a bunch of radicals, and these radicals will serve to start our polymerization. So what happens next? Well, we'll talk about growth. And growth occurs in radical polymerization when this radical interacts with some kind of double bond in a carbon monomer. So we might have our radical right here with our unpaired electron, and this might come close to, for example, if we had two carbons double bonded to each other. I'm going to omit the hydrogens coming off. Think for a moment, what was this monomer? Ethylene. So if we polymerize this ethylene right here, we're going to have polyethylene. So what happens to the electrons? Well, this double bond is composed of one sigma bond, which is quite stable, but also a pi bond, which is susceptible to attack. Attack from what? This lone, unstable, unpaired electron associated with the radical. So what happens to the electrons when this radical approaches this vulnerable double bond? Well, the electron from the radical and one of the electrons from the double bond interact with each other and create a new bond. Meanwhile, this creates the other electron associated with the pi bond from this carbon-carbon bond, then it becomes unpaired. And what happens as a result? Well, we get our the radical group, and we have the two carbons here, and then this one electron that became unpaired now is a new radical on the end of this carbon chain. All right, well, that's one step of so I guess this could be considered part of the initiation process. Right now we're in the process of growing, so we've added one ethylene monomer. Well, what happens next? Well, there's still this radical right here, and another ethylene, monomer could come by and start interacting. So, for example, we could have our second ethylene monomer. They're double bonded to each other, but now this double bond is vulnerable to attack from this polymer. So we get the same thing happening. And then we still have our free radical on the end. So this can continue, and in fact it does continue, like thousands and thousands of times, until we've built up huge long chains of polyethylene or any of these other double bonded species with potential vinyl groups or other side groups off the side. So before, remember how we talked about we could have PVC, or we could have polystyrene, or we could have polypropylene, or we could have any of those fluorocarbons that we could make to make things like Teflon. So, so that is the growth step of radical polymerization. Okay, now let's talk about the interesting, and if we're going for high molecular weights, sad part of radical polymerization, termination. So what happens during termination? Well, there are actually a couple different ways that polymerization can be terminated. So we'll talk about 3 of them, or I guess 2 of them are terminations, and then 1 of them is related to termination, but a process that is usually undesirable. So the first thing we'll talk about is combination. So what happens with combination? Well, we could have a radical group and some number of polyethylene monomers. We might, for example, say we have N on one chain, and then and there's a free radical on the end. Simultaneously, there's some other polymer chain that maybe has M monomers in it. These 2 unpaired electrons, if they're brought close to each other, say, hey, I'll anthropomorphize them. I'll say, hey, we would like to connect with one another. What happens when we connect with one another? Well, they end up just becoming a single bond between these 2 carbons associated with them. So what does that look like? Well, we have our radical, the radical from our initiator, a big long chain where we had N, the connection, and then another chain where we have M, and then the radical on the other side. So this does nice things in the sense that we've created a molecule that had twice the molecular weight of any of its components, but the downside is now there's no place for more growth. And that's unfortunate. So if there's no place for any more growth, we've basically locked in this polymer at its particular size, and we can't increase its molecular weight any further. So now let's talk about another option for termination. So like combination, it involves 2 free radicals from growing chains interacting with each other, but this one has a different name and a different process. So this one is called disproportionation, D-I-S. Disproportionation, and this involves if we had some radical and we had a chain of length N on it and 1 free radical going on it, and then we also had, for example, let's say another a radical, and this could have had M monomers, and then this one has a free radical on the end. So there's a little bit of trickiness that involves that goes here. So this involves 2 free radicals neutralizing each other, but unlike combination, where they just jump together and create one of a big length, here the 2 chains stay at approximately their original lengths, but they both neutralize each other for further polymerization. So what happens with this? Well, let's draw some of the hydrogens because those are actually important for this process. So we'll sketch 2. So this carbon at the end, this would have 4 things connected to each other. The other carbon, 2 hydrogens, and then the free radical would be a thing. And then this carbon would also have 2 hydrogens on it. And then this carbon next to this other one might also have 2 hydrogens connected to it. So what happens during disproportionation? Well, this free radical ends up coming over here and interacting with this hydrogen right here. And when it interacts with this hydrogen ends up getting kicked off. It belongs to this chain now. And so we get three hydrogens connected to this carbon. And then what happens to this over here? Well, we pulled off a hydrogen and then put in an electron. Then we have an electron here and an electron here. So we end up getting a double bond at the end of this chain. And here we have no free radicals, so neither chain can polymerize any further. Now, strictly speaking, I guess maybe if some initiator found this double bond here, it could sort of reopen the polymerization process, but these are generally exceedingly rare compared to all of the monomers floating around, so that basically doesn't happen. So once you get disproportionation happening, you basically you cap off one chain, you cap off another chain with the double bond, and the process of polymerization is halted. All right, so now we're going to talk about the third option. Strictly speaking, this doesn't halt further molecular growth, but it's something it is a process that is related to these other things. So let's talk about it now. So we're going to talk about backbiting. This is seriously the chemical term they use for it. So what happens with backbiting? Well, you can imagine we might have our initiator, and then we might have some polyethylene chain growing off of it. We might have a case where we have, let's say, one carbon out here on the end, and then another carbon that is down here. And let's draw some of the hydrogens associated with the carbons of interest. So here we have a free radical and two hydrogens, right? So hydrogen is going to have, or the carbon's going to have four things attached to it: hydrogen, hydrogen, a free radical, and the connection to the other carbon. This carbon also has two hydrogens connected to it because its remaining two bonds are connected to its two neighboring carbons. So what happens? Well, polyethylene chain, I've kind of drawn them in nice, neat rows, but we know that all of these bonds, they're all flexible. Not too much from stretching, but reasonable amounts of rotation are allowed between adjacent carbons. So we could imagine if this chain is long enough, eventually this free radical could bump into the carbon back on itself. So what might that look like? Well, if we have this electron that could come in and interact with this carbon earlier in the chain, we might have a case where our chain then looks something like we still have our carbon at the end, and we also have this carbon here. So what happens when this radical electron comes to visit? Well, it pops off one of the hydrogens here. So we still have this hydrogen, but maybe it pops this hydrogen off here, replaces it with the free radical, and the hydrogen that was here ends up being connected to the hydrogen at the end. So this end here gets capped off with a hydrogen. We have a free radical now in the middle of our chain. So what can happen? Well, we still have a free radical available here. So what happens? Pause the video and think for a moment. What happens if this free radical would then interact with some of the ethylene monomers floating around in solution? Well, what's going to happen? Well, this site would now become the active site for further polymerization. So we'd have this silly side chain where nothing's going on, but we could have further polymerization from this chain. So what would happen with more monomers added? Well, if more monomers are added, then we would get we'd still have this chain, but then we could get further growth off of the site where backbiting occurred. Now, question: is this process good for mechanical properties? Spoiler alert, no, it isn't. And why isn't it good? Well, if you think back to when we were talking about molecular interactions between chains of adjacent polymers, if we have lots of side groups coming out, then chains can't pack very evenly, so we get dead space around the side groups. So these short side chains coming off of our main new backbone of our polymer are generally bad for mechanical properties because they decrease the density with which we can pack chains and decrease our adjacent chains' abilities to interact with each other. All right, so we might have two main goals when we're polymerizing things. Our first goal, as we were just talking about here, is often good mechanical properties, which is usually associated with a high molecular weight. So usually we want a high molecular weight. Oftentimes, we might have some control over our, we might, as chemical engineers, have a choice to control our three processes in our polymerization. We might be able to have some control over initiation, growth, and termination. So if we're thinking about these three processes, my question is, which process or processes do we want slow and which do we want fast? If our goal is to make a high molecular weight polymers. All right, so the answer is we probably want to suppress termination, or in particular suppress the rate of termination to be as slow as possible. So that way, if termination is slow, then there will be a lot of growth of polymers before those get a chance to happen. Alternatively, we could also suppress initiation too, so that way there are fewer chains competing for the monomers that we do have. But suppressing termination is the key thing to getting high molecular weight polymers. In addition to getting high molecular weight polymers, we also might want to have our polymerization process produce polymers all of approximately the same size. So we talked about that a little bit earlier when we talked about how we quantify molecular weight. And one way of quantifying how what the spread of molecular weights is to talk about the polydispersity index. So in general, we want a low polydispersity index, because that means we'll have all of our polymer chains will be approximately of the same molecular weight as each other, so that way we know we have homogeneous properties. And the way in which they interact with their environment will all be the same, so we can create more reliable biomaterials products. So if we want a low polydispersity index, which processes do we want slow and which do we want fast? So my question is the same as this one, only this time we're trying to get low polydispersity index. Well, it actually turns out to be basically the same answer. We want to suppress termination, so that way all of the polymers can have as long as possible to grow, but simultaneously, in this case, we also want our initiation to be fast relative to growth. So if there's a fast initiation step, then all of the polymers start growing at the same time, and then they all have approximately the same amount of time to grow before they're all terminated. So we want fast initiation too for polydispersity index. So oftentimes as engineers, we might have trade-offs between growing large polymers and growing dispersed polymers with respect to how fast our initiation is, but both of these things we want to suppress termination as much as possible. One last thing we might want to do as bioengineers is to create block copolymers. And what do I mean by block copolymers? Well, I mean something like we have a whole bunch of one type of monomer, and then we get a whole bunch of a different type of monomer, and then we go back to making a whole bunch of one type of monomer, and this process could continue for some amount of time. Only instead of just like 5 or 6 of these, we might have hundreds or thousands of these block sizes. So what might be the benefit of doing this? Well, if we have one set of monomers that are all hydrophilic, and then another set of monomers that are hydrophobic, a lot of times we can get these polymer chains to assemble into cool structures. So we might have a bunch of hydrophilic stuff, and then a loop of hydrophobic stuff that all likes to interact with itself, and then the hydrophilic end likes to interact with another hydrophilic end, and then the hydrophobic end. So we can end up having control over somewhat medium scale properties by just controlling the hydrophilicity, hydrophobicity, and also the length of the copolymer chains. So a question to think about is if we have chain life on the order of milliseconds, 10 to the minus 3 seconds, is if we have chain life on the order of 10 to the minus 3 seconds, is block copolymerization possible? The answer is no. We can still do copolymerization, right? We can still dump in a bunch of A's and a bunch of B's, but if we have short chain life, which is the case with free radical polymerization, then this we might only be able to get something like A, B, B, A, B, B, A. We can still copolymerize things, but we can't get these large structures of a bunch of A's and then a bunch of B's and a bunch of A's, because the chances of this happening on its own randomly basically never going to happen. So we can't get nice block copolymerization. We can still copolymerize, but it's got to be random. Got to be random. So how can we get copolymerization? Well, we got to increase the chain life for more than a millisecond, right? If we only have a millisecond of chain life, there's no way we're going to be able to be like, okay, slow down. I'm going to put in my B's now. Okay, still stay alive. Then I'm going to put in more A's. Like, it's done before that ever happens. So we need to figure out a way to get this chain life to be more than 10 to the minus 3 seconds. So the key to all of this working, high molecular weight, low polydispersity index, and controlled block copolymerization, is suppressing termination. And the key to suppressing termination, well, this involves taking a careful look at reaction rates. So we'll look at kinetics, and kinetics will inform what our best strategy is for how to suppress termination. Spoiler alert, it's going to be through this process called ATRP, or atom transfer radical polymerization. So we're going to do atom transfer radical polymerization, and that's going to suppress our termination. And by suppressing our termination, we're going to have all of those great outcomes like we talked about earlier. So first, let's look at the steps of free radical polymerization, and then we'll talk about where ATRP can come into play in order to do that. So we talked about earlier, we talked about the free radical polymerization as an initiation, a growth, and a termination. We kind of drew sketches. Now I'm going to talk about things in terms of rates. So rates of initiation, growth, and termination. So this first step for initiation is actually it's actually sort of like two steps. So we'll break this up into two parts. First, we need to create radicals. And the creation of radicals, this rate of radical creation is equal to 2 times a dissociation constant times some factor F, which I'll talk about in just a second, times the concentration of initiators. So what do I mean by initiators? Well, by initiators, I mean the concentration of these benzyl peroxide species. And the rate at which that happens is the rate at which light and heat cause these things to break apart into their free radical components. So the more of these benzyl peroxide molecules there are around, the higher the rate of radical creation. So what do I mean by these brackets? By brackets, I mean concentration of this thing. And then here, this is a rate constant, and that depends on temperature, light, etc. So we can play around with our rate at which radicals are created by increasing our concentration of radicals. So the more initiators we have, the more chance that at any given time some of these initiators are going to break up and create radicals. Similarly, if we can tune our rate constant, this would increase the rate at which any one particular molecule would break apart and form the radical species. So what is the second step? So this rate of radical creation would basically be the step of an initiator going with some dissociation constant into two radicals, 3 radicals, something like this. All right, now last thing, what is this factor? What is this F? Well, sometimes we can think of it as sort of an efficiency that sort of sweeps a couple of different chemical processes under the rug. So this is basically between 0 and 1, and if we had an initiator break apart and form 2 radicals, but then those radicals immediately combined back with each other, or those 2 radicals just disproportionated single monomers, or they created monomers and those monomers like and immediately combined with one another and disproportionated. This is sort of an efficiency factor that says, okay, yeah, I know that my initiator is forming radicals at this rate kd, but this describes the effective rate of radical creation, i.e. the radicals that only the radicals that end up forming effectively growing monomer chains. We talked about initiation. Now we're going to talk about the rate of propagation. So, we talked about the rate of radical creation. Now we're going to talk about the rate of initiation. So, this is going to extend down here a little bit. So what do I mean by the rate of initiation? Well, we have some radical. This would be this species here that has that doesn't have any monomers combined with it yet, but still has this free radical that's going to go on and do this chain reaction. This radical might combine with a monomer. This monomer would be like a single ethylene molecule, and with some rate k sub I, these two combine to form a radical monomer complex where the free radical is now on the end of the monomer. And if we wanted to talk about its rate, the rate of initiation, then that would be equal to the rate constant ki associated with this process happening times the concentrations of the concentrations of both of the components that go into it. So there'd be the concentration of radicals and the concentration of monomers. And the idea is the rate at which initiation happens is going to be proportional to the concentrations of these two things. So the more concentrated the monomers are, or the more concentrated these initiating radicals are, the higher the chances are that any two of them are going to bump into each other at the right time and be able to form this RM complex. And there's this proportionality constant that, again, is also dependent on temperature and on some other factors that describes if the two components bump into each other, they need to bump into each other with enough energy to proceed through the reaction. So the more concentrated your radicals are and the more concentrated your monomers are, the faster this process. All right, next we're going to talk about propagation. So when we talk about propagation, we're going to frame things in similar ways to chemical reactions like this. Only in this case, instead of just having a radical and a monomer, here we have a radical and a monomer chain attached to that radical of length n, and then on the end of it, there's a free radical. And this thing combines with some monomer, and that goes on to form a radical with a monomer chain length of n plus 1. So it's just the process of adding this monomer on and then popping the radical over to the end of this slightly more grown chain. And if we were to talk about its rate, there might be some rate constant here, which will do k sub p for propagation. And pause the video now and try to figure out what the form of this rate of growth might be. So we can talk about the rate of growth. Well, the rate of growth will have its rate constant, k sub p for propagation, and it will be proportional to the concentrations of its components that go into it. So it's going to be proportional to Rm sub n times the concentration of monomers as well. So the higher concentrated our monomers are, and also the higher concentrated our growing chains are, the faster growth is going to happen. Similarly, if we have a high rate constant for this reaction proceeding, growth will also increase. Now, finally, our last thing, so this is propagation. Our last thing is going to be termination. So termination. Well, what is the process of termination? So termination is two of these chains, let's say of length n with radicals on the end, combining with each other with some rate constant kt to form, and they could form kind of any of the outcomes that we talked about earlier, for either via disproportionation or combination. So they might form r m sub 2n r, or they might also form r m sub n with a hydrogen and r m sub n with a double bond at the end. So because we don't really care too much which of these processes terminated, we'll just characterize it with a single reaction rate, k sub t. Now, pause the video and try to work out what the rate of termination would be. All right, so we can still use the same form that we did earlier. So there's going to be the rate constant out front here, and it's going to be proportional to the product of its constituents. Well, here we need two of these growing chains, so we could think of it as r times the concentration of r m sub n with a radical times the concentration of r m sub n with a radical. Or we could just as equivalently say, hey, well, these are actually the same thing. So it's like k sub t times the concentration of actively growing chains squared. So the rate of termination is proportional to actively growing chain concentration squared, whereas the rate of propagation is proportional to the concentration of actively growing chains times the concentration of monomers. Usually the concentration of monomers is quite large, so this process happens frequently, but this process does happen enough for, well, polymerization to end. All right, so now here's a question to think about. What happens to the rate of propagation if we double the concentration of actively growing sites? So take a moment, pause the video, and think about that. Well, the answer is we double our rate of growth, right? So that's great, right? Didn't we want to double our rate of growth? You know, if growth is fast, then we'll get longer chains, right? Right? Well, let's think. So if we took here's our equation for rate of growth. If we double this number, then we'll end up doubling our rate of growth. So that's good, but there's a catch. So we'll think about that in just a second. All right, so here's maybe the downside. What happens to the rate of termination if we double the concentration of active sites? So pause the video and think what the consequence of doubling our concentration of active sites is for termination. So what's the answer? 4 times the rate of we get 4 times the rate of termination. Sad face here. So if we want to double the rate of growth, we must quadruple the rate of termination. And this is really bad. Wait, why is this quadrupled? Where does the quadrupled come from? Well, if we look at the rate law for termination, the rate of termination is proportional to this concentration squared. So if we double this number and then square it, we quadruple the rate of termination. So if we quadruple the rate of termination, but we only double the rate of growth, what's going to happen to the average length of our chains? Well, the average length of the chains is going to go way down, and we'll be able to quantify that later. But the idea here is if you double the number of active sites, you're going to greatly increase your termination while only mildly increasing your propagation. And that's generally bad for increasing molecular weight. All right, so now here's the question. how do we lower the concentration of active sites? Well, if we lower by lowering the concentration of active sites, then that will increase our molecular weight. So that's what we want. But the question is, how do we do that? Well, one strategy for doing that would be to just lower the concentration of our initiator, right? If we lower the concentration of our initiator, then we're going to be creating fewer of these radicals. If there are fewer of these radicals to begin with, then we're only going to have a few chains growing at any given time. And if we only have a few chains growing at any given time, we're going to be able to greatly reduce this this termination rate. So our naive strategy is to lower the concentration of our initiator. But what might be some downsides to doing that? Think for a moment. What might be some downsides to lowering the concentration of our initiator? Well, one downside is it makes our overall process slow. Right? So if we only have a couple of actively growing molecules, it's going to take forever for the thing to polymerize. All right. But, whatever. I mean, if it ends up being a second rather than a millisecond, sure, who cares? That's fine. So maybe this actually isn't that big of a problem. But what about our thoughts about copolymers? We still can't do copolymers, right? It would be really tricky. We would need to drastically lower our concentration of initiators in order to have any appreciable amount of time to pipette in our new B monomers after our A's are depleted. So this strategy of lowering the concentration of our initiator, I don't think it's going to work. Or at least work well enough to do what we want to do. So what can we do? Better. Our better strategy is to do ATRP. Oops. ATRP. ATRP. So our better strategy is to do ATRP, or atom transfer radical polymerization, like I talked about just a second ago. And that's where we were going with our discussion of radical polymerization. So, what's the key to ATRP? Well, ATRP is this atom transfer part. So what do I mean by atom transfer? Well, let's say we have a reaction in equilibrium. So we have something going forward and going backwards, and it's going forward with some rate constant. I'll do k sub a, and it's going backward with some rate constant k sub d. So on the right-hand side, we have our radical combined with a monomer chain of length n and the exposed radical on the end of it. And in addition, so this can freely polymerize back with itself. So we could, this can feed back on itself with monomers, and with monomers this would become Rmn plus 1 with the radical exposed. But instead of just having this process happen a whole bunch of times by itself, we add in this this atom transfer compound. So it's copper typically with a 2 valence and 2 bromines. So it's copper 2 bromide, but then there's also this other this other complex attached to it, BIPI. I won't get into the details of what is this, but this is some organic molecule with some nitrogens in there and stuff like that. Anyway, this BIPI just sort of helps facilitate this forward and reverse reaction. So here we have actively growing monomers that are feeding back on themselves, becoming our Mn+1s when monomers are being added to them. And also existing is this copper bromide with this other complex on it. So what's on the left-hand side of this equation? Well, on the left-hand side, we end up with copper 1 and only one bromine, and this ligand, this facilitating molecule on it. And so we had two bromines over here. We only have one bromine over there. What happened to this bromine? Well, this bromine capped off the exposed radical end. So here we have no radicals, and here we have this radical that's leading to active growth. So, while active, we have R in our radical plus one monomer going with our propagation constant to R N+1 with a radical on the end of it. So that's this looping process. And also, we have two of our actively growing chains combining together with our termination to either do, we could describe it sort of as two processes. Instead of one KT, we could say it's a KT in combination to form, so this is like two of these chains combining together and the two radicals forming a single bond. Also, it could be the K for termination by disproportionation, which we talked about earlier, where one of the chains gets a hydrogen on the end of it, and then the other gets that double bond at the end of it. So regardless of which process this is usually undesirable for creating high molecular weights. And oftentimes, we don't really care about which of these processes is happening, so we'll just lump them together with a single K sub T. So now let's think about, so both of these processes are happening when the actively growing chains are on this side of the equilibrium. But while this is happening, so maybe a monomer grows a little bit and then undergoes this reaction, and it kind of puts it in this state where it's capped off with this bromine. And when it's in this state, we might say it's in the, we might say it's deactivated. Why is it deactivated? Well, there's no radicals now. The radical kind of got gobbled up by this copper 2 becoming copper 1 in this case. And here, it's activated, so it has the radical exposed, and it can do this growth process. So we can define an equilibrium constant, right? Anytime we have equations where there's a forward and a reverse, or an activated and a deactivated sort of reaction happening, we can define an equilibrium constant. And we'll call this K, capital K, ATRP, and it's going to be equal to Ka over K sub D. So my question is for getting high molecular weight, do we want large or small k ATRP. So the answer is, well, we can think, if we want to, what is the consequence of having a large or small k ATRP? Well, it depends on whether this reaction or this reaction is, this reaction or this reaction is favored more with each other. And if we have a low k ATRP, if we have a small k ATRP, then the then deactivation, i.e. little k sub d, is favored. And if the deactivation is favored, what does that mean? Well, if deactivation is favored, then it means that most of the polymer chains are going to be capped off at any one given time. So if most of the polymer chains are capped off, then only a few are growing at a time. So what does that mean if only a few are growing at a time? Well, it means, yes, we suppress our growth, but we greatly suppress termination. So if the deactivation is favored, then we lower the concentration of our, then we lower this concentration. And our whole goal of this, of our process to increase molecular weight is to lower this concentration, because we suppress termination a lot, right? Remember, that was our concentrations, that was proportional to our concentration squared. And we only suppress growth a bit. And if you recall, that was proportional just to concentration to the first power. So if we suppress, so if we have a, if we can tune our ATRP equilibrium constant to mostly favor this, then only a couple of the chains are actually actively growing at the same time. So that means that the chances of any of those two actively growing chains bumping into each other and canceling any future polymerization is actually quite low. And that's what we need to really suppress termination and get high molecular weights. So thanks for watching, and freely polymerize. Thanks for watching.